Okay, so I think we can get started. Our speaker is already here. Hello and welcome everyone to another series of Astronomy Sundays. We appreciate you joining us from all the corners of the world, whether it's morning, noon, or evening. We really look forward to an engaging session together. So, without further ado, let's get started. So, for all those who are new in today's session, let me quickly introduce you to the club. Astronova is an astronomy club formed in partnership with IEEE societies and student branch chapters at the University of Calcutta. This club has been established by a group of students passionate about astrophotonics, astronomical instrumentation, space sciences, radio astronomy, and astronomy in general. And the club regularly organizes events related to these areas. And Astronomy Sundays is part of such an event where, in every session, we aim to bring experts from diverse fields in astronomy and engineering to share their valuable insights with us. I am Sonia Ghosh, and I will be your host for today. And a bit of introduction about myself. I'm a second year PhD student at Kaptan Astronomical Institute, affiliated to University of Groningen. I am working with science-driven simulations for 21 centimeter cosmology from the moon. Uh, just to check once, can you guys hear me?
Yes, I can.
Yes, we can.
We can
Yeah,
hear
sure, we
you.
can.
Okay. Can anyone please confirm if you can hear me?
Yes, I can hear you, Sonia.
Okay, great, thank you. All right. Okay, so now let's proceed to the introduction of our esteemed speaker for today's session. Our speaker originally hails from Nabogram, West Bengal, which is somewhat the eastern part of India. And many of you who are residing in different parts of West Bengal might be familiar with this place. He did his BTech from IIEST Shibpur, following which he pursued his master's from University of Virginia. And finally, he completed his PhD from Caltech in 2000. Currently, he is a senior scientist at the NASA's Jet Propulsion Laboratory, California, Caltech, Pasadena. His research interests include microwave, millimeter wave, and terahertz receiver systems and radars, and developments of space instruments for the search for life beyond Earth. He has more than 375 publications in international journals and conferences and holds more than 20 patents. Throughout his career, he has garnered numerous awards and widespread recognition, reflecting his exceptional contributions and expertise. So, let us please welcome our speaker, Dr. Goutam Chattopadhyay. Would you prefer to answer questions during your talk, or would you like to address them?
It might be better to actually keep the question and answer, towards the end
Mm-hmm.
after the talk ends. But what I am planning to do is maybe not spend a lot of time giving a formal talk. I, of course, give I'll introduce some of the stuff that we have been doing.
Mm-hmm.
But it might be I want to have more time to have question and answer, so that if you have questions, not that I have all the answers, but at least we can have some kind of discussions. That will be a good thing.
Okay, that's great. Yeah. Okay, so everyone, please feel free to write your address in the chat box during the session, and we can address each of them after the session in the question answer. So once you're ready,
Yes. Okay. I'm really excited to talk to you all. Thank you all for coming to this. It's early morning here in Pasadena, California. About right now it's about 7:08 a.m. And I know in Kolkata right now it is extremely hot. But here outside temperature is about 11 degrees centigrade, kind of cool, sunny, California, but it's kind of cold. Um, Okay, so let me start my slides and okay, let me share my screen. Select Windows or screen, entire screen, allow. Okay, can you see my screen?
Yes, we can.
yes,
Okay, let me make it full screen now so that you can see my slides only. You can see only my slide right now, right?
Yes.
Okay, good. All right. So what I'm going to talk to you, I know this is an astronomy club, but I'll talk a little bit more about planetary science and also a little bit of astronomy as well, because I build instrument at some millimeter wave and terahertz frequencies for astrophysics, planetary science, as well as Earth observing science. So we cover all these areas. Um, let's get going. So before I start, I want to talk a little bit about NASA JPL. Many of you know that NASA has centers all across United States. JPL, let me have my pointer interruption, laser pointer. Okay, so JPL is on the west coast, but our headquarters is in Washington DC in the east coast. JPL is the largest NASA lab for robotic missions, and all the different labs that you see at different places, they have different roles to play. In Houston, Johnson Space Center, that is primarily we are dealing with man-made missions, that is for astronauts and stuff like that. So this is JPL. We are a NASA lab, but it is actually run by Caltech, managed by Caltech. We have about 5,500 people on our lab, and we have about $2 billion dollar per year budget. If you think about it, it is not as much compared to what we do. So hopefully in future the budget will go up. So if you look at this slide here, I'm showing that all the different missions that are ongoing currently, and these are all in just white, that's already there in space, and the one in little bit lighter color, they are on planned missions that we are going to launch in near future. So that all of them are where JPL is involved. So that can tell you that we have been really busy and building all different kind of instruments here at JPL, and I am always excited because I have been involved in many of these different missions. And in terms of some flagship missions, many of you know that Voyager 1 and 2 was launched long time ago, and then it's are outside our solar system right now. And then Cassini was one of the biggest missions that we developed here at JPL that went to Saturn, and different rovers, Curiosity Mars and Europa Clipper. Right now it is just being assembled in the high bay that is going to go to Europa, moon of Jupiter, and helicopter Perseverance rover also built here. And few examples like Voyager, as I said, Voyager was right now it is about 42 you know is 45 billion kilometers away from Earth. Voyager 2 is about 37 light hours. Of course, we generally talk about light years, but this is about light hours away. So just in comparison, our sun from Earth is 150 million kilometers away. That will tell you that how far This is the farthest a man-made object has ever traveled. And recently, you must have read in the newspaper that we had some glitch in the system. So it was not really sending data back, Voyager 1. But recently, we were able to fix it from sitting here. And now it is actually started sending again, good data. Of course, data rate is really low because it is so far away and the power is not as much. And there is the Magellan went to Venus. That was again an amazing system. That was the first time we had a radar that we could, because you know that Venus is very hot and is a very thick atmosphere, that before Magellan went to Venus, we didn't know how the surface of Venus looks like because of the atmosphere. But through a radar that we built here at JPL, we were able to actually map out. That was a synthetic aperture radar, and it also had an altimeter and radiometer. And then many of you know that Galileo that went to Jupiter, we had a very high gain antenna. That was the first time we used a deployable antenna for communication. This was not for science, this large antenna. However, it actually did not deploy after it was launched. There was a malfunction. And as a result, we could not get all the data through this high gain antenna. Instead, we had to use the low gain antenna so that the data rate that came from Galileo was much lower rate. That it means it took longer time to get all the data. So before I start, talking a little bit about what I do, I want to really acknowledge one person, Professor J.C. Bose, who hailed from Calcutta, of course. Many of us know, we grew up reading about him. He is considered the father of the modern wireless communication. And I really want to acknowledge, because we have been following his path. He started the first millimeter wave, wireless transmitter system. And right now, millimeter wave is big in every communication system. And I work in terahertz frequency sub-millimeter wave. We have been following his path. And one of the things that I show this slide to tell you that if you look at a modern smartphone, what it has replaced, all this stuff, all this mass and power that we can see, camera, phone, all those stuff has been replaced by a small device that shows the power of modern day electronics. Okay, let's start with the Big Bang theory. This is not the Big Bang theory you watch on TV. This is the real Big Bang. And of course, since you are in the Astronova Club, you all know about Big Bang theory. As you know that the modern theory that our universe started with the Big Bang about 13.85 billion years ago. And then the modern universe was about, started here about 8 billion years after the Big Bang. And so this is relatively very modern. But the first light of this universe actually came out about 380,000 years after the Big Bang, and that light is called cosmic microwave background. The reason for that was that at the beginning, the universe was a very big hot plasma, and no light can escape. But the first light, that decoupling happened, that came out at this time. And it is very interesting. I tell this story about how it was discovered that two scientists at AT&T Bell Lab, Bob Wilson and Penzias, they're doing a communication experiment at millimeter wave in 1960s. And what was happening is that whenever they were looking at the received signal, they were getting some extra noise. You know that when we receive signal, there is some noise associated with your receiver system. And they were not able to, wherever they looked, the same noise was still there. So they were scratching their head thinking, what's going on? And, what we do we do a lot of experiments in the lab, right? And when we cannot explain something, what do? We think it must be experimental error. And then we just increase our error bar. But those two guys, they were very smart. What they did is they went back and started thinking about it, and they realized what they were looking at was the first light of this universe. And for that, they went on to win the Nobel Prize in Physics. And so what I tell you all students who are listening in, that next time you do some experiment and you cannot explain something, don't think it's experimental error. You never know, you might win the Nobel Prize. So in terms of astrophysics, planetary and earth sciences, you know that life cycle of our universe, that's actually how the stars and galaxies are formed. There is a great, that stars forming gases are there, that from there stars are formed, and then that it evolves in a supernova and evolves stars, and then it becomes that outflow, nuclear activity happens, gas cooling happens, then when the nuclear, it becomes a supernova, and then it actually collapses. So this cycle actually continues, but we really don't understand very well all these processes, that how the stars are formed, how galaxies are formed. So high resolution spectroscopy allows a detailed investigation and mapping of different processes, and we are doing those. And submillimeter wave and terahertz plays a very important role in this exploration. And one of the then question is, how did we get here? And the water trail, water plays a very important role about life. And then, but still we do not know how the solar system water as well as another system water has originated, from where it has come. So these are very exciting areas of research that is ongoing. And one of the biggest questions that we are trying to answer is, are we alone in this universe? That whether the life really evolved only on a single planetary body, or has it evolved somewhere else in whatever form. So these are these big questions that we are trying to really answer through our this different instrumentation development. So question about that, are we alone in this universe? So let's look at this from a back of the envelope calculations, because people ask me, what do I think? So if you look at these, our universe, like our Milky Way galaxy, we are part of our Milky Way galaxy, and we have about 100 billion stars in our own galaxy, in each of these galaxies. And of the order of magnitude, we have about 100 billion galaxies in the observable universe, which means we have about 10 to the power, 1 billion, 100 billion is 10 to the 11. So 10 to the power 22, about stars in our observable universe. And we are finding that many of these stars, the majority of these stars, they have planets around them. We call them exoplanets. And the question comes is, what is the probability that we find one such planet in these trillions of trillions planet, where conditions are such that life can exist? Now, that probability has to be a non-zero probability, and that's what actually we are very much interested in. So far, we have found about this number 5,612 is just our last month's number. So we found this many in exoplanets so far, and many of them are in the habitable zone. What do you mean by habitable zone? Habitable zone are the one where the surface temperature is such that water can exist in the liquid form on the surface. We call that in the Goldilocks zone, and that's what we are actually looking for, planets which are like our Earth kind planet, which are not gaseous giants like Jupiter. We know that that cannot hold life, but rocky planets like Earth, and many of them are actually rocky planet and in the Goldilocks zone, and they have in the habitable zone we are finding. So that is the thing that we'll have to explore more. But our knowledge is limited. Our instrument capability is limited, because we'll have to find out, is there an atmosphere there? How do we actually do the next step? Because the nearest such planet we found, which is in the habitable zone, is about 4 light years away. As I said, if you remember the 45 billion kilometers, our Voyager 1, it is only, some light hours away. So if you think about light year, that is really far. So with modern day technology, we really cannot go to those planets. So we'll have to develop instruments so that we can explore them, understand them, sitting here on our planet Earth. So you might ask that I mentioned about trillions of exoplanets. How come we found only 5,000 plus? The reason is we haven't looked far and beyond. This is our Milky Way galaxy. We have looked only in a very narrow area of our own galaxy so far, because that's our limitation of our instruments, that we cannot really explore, find these planets around star that easily. And that's our challenge. So, but let's look a little bit in our own, solar system. That can life exist in our own solar system? And the answer is yes, there is possibility. Look at this is Enceladus. Enceladus is the life. This is a moon of Saturn, and there's an instrument. The mission was Herschel Space Observatory, and there's an instrument called HiFi. I actually was involved in building that instrument, HiFi instrument, and we found with that instrument that water is gushing out from Enceladus. So this is a very cold planetary body. If water has to get, gush out, which means it has to have a source of energy that is keeping this water in the liquid form. So if there is water, if there is a source of energy, is there life? What else is coming out in this? We don't know. So NASA is thinking of a mission to go to Enceladus and really explore what else is coming out. Is there organics? Organics does not necessarily mean life, but that is the precursor of life. So these are, exciting missions that we'll be working in the future. Another very interesting planet is Europa. As I said, Europa Clipper that we are building right now. So we'll do some of these experiments. So Europa has the best chance of having life there today. The reason is we believe this again is a very cold planetary body, ice, discovered with ice. But scientists believe that there is a liquid water ocean underneath the thick ice shell, which means there is a, like our own, planet Earth, there is a mantle, there is source of energy that is keeping this water in the liquid form. And the thickness of this ice shell is about 15 to 100 kilometers thick. In some places, thin, but other places thick. So the question is, if there is, water like this, is there life? So if NASA comes to you and asks that, okay, we are planning to send a mission to Europa to find out if there is life, what kind of instrument you are going to build? The obvious answer is, okay, we are going to send a drill a hole, lower a bucket and see if there's any fish. Unfortunately, it takes about 7 years to go to Europa. And when you build such instruments, the total amount of DC power available to us is about 300 watts. 300 watts is 3 light bulb worth of energy. So that is not enough to drill a hole, which is about 15 kilometers to 100 kilometers thick through ice. That means we'll have to do something else. And yes, there are some other ways to do this because there are a lot of cracks in this ice and that the material goes all the way to the top, but it's so cold it freezes. However, we all know that Europa is close to Jupiter, and Jupiter has very high magnetic field, which means very high radiation. What radiation does, it actually sputters all the material in the atmosphere. So you can do high resolution spectroscopy to see what all this material that is coming out in the atmosphere and see if there is any organics or not. So, and also we are sending some GPR, ground penetrating radar, to map it out in the different layers of these to understand. So it's a long way to go to answer those questions, but at least we have started taking baby steps towards that. So, and you all know that we keep going back to Mars, because if you look at Mars, one of the reasons that we go back to Mars is because Mars is the nearest planet, easier to go compared to other planets. And on the other side, from scientifically, actually resembles, at least in its early history. The question that we are trying to answer is, was Mars ever habitable? Is there life on Mars today? Was there life on Mars at any point of time? We don't know that answer is. One of the things I want to be very clear that whatever you read on the internet or see on YouTube about aliens, that we have not found any form of life, not even a single cell, anywhere outside our planet Earth. Nothing. So please don't believe all this that you read. So because if indeed that is true that there is some aliens, then we can stop spending billions of dollars and building instruments to try to find life somewhere else. So that's what is my request to you all. So to explore Mars, we have been building all these rovers over the years. Pathfinder 1996 and Spirit Opportunity, that twin rover in 2003. You can see the size of these are all scalar model, exact size model of those at JPL, and Curiosity 2011. And then going to Mars itself, again, we have the Perseverance rover. I'll show you the picture of that. But going to Mars is not easy. It is, and landing on Mars is not easy at all. What are the challenges? You can see here that we can launch these missions to Mars only once in 2 years, because there is a window of about 2 to 3 weeks maximum, where the distance between Mars and Earth is the closest, so that we need minimum amount of fuel to reach there. So look at this. This is the Perseverance rover that we sent. So July 30th, we launched, and at that time, Mars was here. So this, the orange, that orbit that you see, that Martian orbit, and the blue orbit is our orbit of our planet Earth, and this light colored yellowish orbit is the orbit of the spacecraft that we did. And the cruising speed of the spacecraft through the deep space is about 77,000 kilometers per hour. So what we'll have to do at this top, at the apex, our spacecraft has to arrive just a little bit ahead of Mars, because if we are a little bit delayed, then we will never be able to catch Mars. So if you come here a little ahead, you can see here the amount of time that it will be coming in there, and then Mars comes from behind after 7 months and it catches up with this, and then we can insert in the Martian atmosphere. So that's where the challenge lies. And on top of that, so Perseverance traveled about 400 million kilometers, and the distance between Earth and Mars about 260 million kilometers. So it can tell you all these numbers, that we'll have to slow it down about 20,000 kilometers per hour when we are inserting in the Martian atmosphere. And Mars is atmosphere is very light. The density of the atmosphere is just 1% of our planet Earth, which means that we do not get the friction, the drag that we need to slow us down. So we'll have to enter in the Martian atmosphere at a very critical angle of 11 degrees so that we can slow it down enough to deploy all this parachute, and then we'll be able to land on Mars. So these are the challenges. And you can see here that all these different sequence that we do, we came up with the idea of a space crane that lowers our Martian, the spacecraft instrument onto the ground, and then it cuts off these threads. So this is, every single step has to go right, and only then we'll be able to land on Mars. So this is we have failed many times. Fortunately, over the last 20 years, we have been 100% successful, because we have more or less figured out, but every single mission is a challenge to land on Mars. And this is the Perseverance rover I'm talking about, the latest rover that landed on Mars. This is in our high bay where we assemble. So this is just before we actually packed it up and send it to Florida for launch for Cape Canaveral. This is we are just doing the final inspection here. So it's amazing. It is one of the most expensive self-driving car you can think of. And it has all different instruments, about 10 instruments, which did a lot of really cool experiments. One of them is MOXIE. Many of you know, actually developed, is actually made oxygen from Martian atmosphere. It already did, it converted the Martian atmosphere to amount of oxygen that can supply a couple of human beings for a few months So it is just that was an experimental basis. We wanted to show that we can do it. And for future astronauts, we can use those oxygen as well as we can use oxygen as a fuel for launch if we need to. So these are the pictures. If I show you and tell you that some of these pictures is one of the roads in Kolkata during monsoon, you might agree. But look at this. These are all from Mars. That is the interesting part. And thing is, we get this kind of terrain only when there's flowing water, which means at one point of time on Mars, there's flowing water. But right now, we have not found flowing water. There is water there underneath the ground, but not flowing water. The question is, what happened? Where did the water go? Can it happen to our own planet one day? And what can we do to prevent it? So these are the big questions that we are actually trying to answer and build instrument for that. So one of the thing I was talking about, I'll give one example about an instrument, about how do we go about building instruments, that how do we innovate. All of you are doing research in astrophysics or in other areas. So one of the things you have to think about, how do we really innovate? You do not wake up in the morning and say, let's innovate something, right? So when you face challenges and then only you can innovate. So here, as I said, for sustaining life, water is one of the critical elements. At least kind of life that we know, hydrocarbon-based life. It could be life, can be of some other kind, but we cannot actively search for it because we don't know what to search for. So water plays a major role. However, we don't know how our solar system water evolved from where it came from. So scientists believe that Earth's water may have come from comets. Comets brought water to Earth. And if I tell you this, you might say, well, how do you prove that? What do you do? It turns out that there are different kinds of water. Water that we drink every day, that is actually H216O. Oxygen has different isotopes. 16 is the most stable one. So H216O is the most abundant water. But there are other kinds of water, H217O, H218O, HDO, and of course the heavy water, 2 deuterium and 1 oxygen makes heavy water that is used for nuclear power plants. So, and all these different waters has their own spectroscopic frequencies associated with them. HDO has one of the line has 509 gigahertz, very strong line. H217O, the strongest line, H216O, the most abundant water, is 557 gigahertz. Then H218O is 547 gigahertz and 552 gigahertz H217O. So all these different frequencies, if you can take the ratio of abundance of different kind of water and measure the D over H, that is deuterium over hydrogen ratio, that can tell you that we find that ratio is very similar what we have on planet Earth, similar to some comets that they're called Jupiter family comets. So if the abundance ratio is the same, then the source has to be the same. So, but we have not done enough measurements yet. So only about 10 such measurements. So the question is still out there. So I will tell you how we are trying to address that. So that is, okay, this is the instrument we are building. And so I came up with this acronym, Water Hunting Advanced Terahertz Spectrometer on ultra small platform. What's up? Because we are trying to answer this question, what's up with water? So what we are going to do is that we are going to measure, as I said, that if you look at the ratio of the measurement that we did so far, many of the measurements are showing that Jupiter family comets has similar D over H ratios on planet Earth. But one of the most recent measurements we did with a Rosetta mission, the 67P comet, where the ratio was completely off, that we really don't know. And 10 such measurements is not statistically significant. So what we said that how can you make a very small instrument and very low power, because we'll have to do this measurement going to a comet and need not land. We can orbit the comet for a close range and then make this measurement. And so But if you cannot send big missions, which cost about $1 billion each, and then you can make only one because of the budgetary pressure that we have. So our idea is that we can build shoebox size small kind of instrument, which is very low mass and low power, and it can get right during a big mission that is going on to Mars. Maybe they can throw us out, and we'll have our own propulsion go to those different comets and then make this measurement. So this is the block diagram of this instrument. This is a sub-millimeter wave instrument. As I said, these different waters, as you see, HDO 509, H218O 548, 17O 552, and 16O is 557 gigahertz. These are the spectroscopy. You remember, many of you are science physics students, but during our 11th and 12th, I think you might remember that we have done spectroscopy experiments using sodium vapor light, because we were able to see the line, the frequency of the sodium using our light spectrometer, because the sodium actually is very high frequency. The line comes out. So this is the system we have. We have to build a very small, low profile antenna. Then we'll have to have a switch to calibrate. I'll talk about this. And then this is heterodyne spectroscopy, which means it is like the radio, where the high frequency, you bring it down to a low frequency, preserving both amplitude and phase, so that you can amplify those signals and then process and do a spectrometer, because you need very high resolution. To do high resolution directly measurement at this high frequency, it gets challenging. Here we are talking about, lambda over delta lambda is of the order of 10 to the power 6, 10 to the power 7. So that's where the challenge comes from. So these are all these different blocks that you have to build, and they have to be low power and low mass. So this is the low profile antenna. These are the challenges. How to make an antenna that is very efficient, but a very low profile, working 557 gigahertz. And then you have to have a switch. If you look around, switch, how you do the calibration is called Dickey switch method. Is if you know for whenever you are doing some experiment in your lab, what do you do first? You actually calibrate your instrument, because if you don't do a calibration, you won't know what exactly you are measuring. So here what we do is that we have a known temperature load. Temperature is equivalent to power, right? If you remember, KTB, K is the Boltzmann constant, T is the temperature of your load, and B is the bandwidth over which you are doing the measurement. That is equal to power, total power that you are coming. So if you actually have known temperature load, that is known amount of power, then if you connect it there, it goes through this system and you measure it here, what is that temperature, that power gives you output signal. And then if you go and do the actual measurement, then you can calibrate against that, right? So this is how it works. However, at this frequency, there is no switch available, no low loss switch available. So we started thinking, okay, you'll have to come up with a new switch. You'll have to design a low profile antenna that does not exist. And many of these components, low power does not exist. Like we built a CMOS SOC based synthesizer that takes low power. And then we had to make back-end spectrometer, which is low power. So target mass and power of this entire instrument is 2 kilogram mass, less than 5 watts of power. How do you do that? Current generation of instruments that are out there, it actually draws more than 40 watts of power. It weighs 20 kilograms. So that's where the challenges lie. So we have to take one challenge at a time. So this is the antenna that I came up with. There are two different antennas we developed. One is a metal reflector antenna working at 557 gigahertz, but it's very low profile. You can see in general, when you have a kind of a Cassegrain antenna, your subreflector is much outside. So that means the volume gets really large. But we cannot put this kind of antenna on a small CubeSat kind of satellite. So we came up with a design where the subreflector is very close to the reflecting surface itself. So I need to work really well. Then we also came up with a low profile lens based antenna. So with a leaky wave feed. I'm using a lot of terms, leaky wave. I'm not explaining them because I don't have time. But if you have question, I can then really explain it to you how all these work. And this is a very thin, antenna. Overall, the entire antenna structure is less than 4 centimeter. Very low profile. If you look at a 557 gigahertz antenna, a traditional antenna, the profile, that dimension will be at least about 20 centimeter. So we have reduced that to 4 centimeter. That's why it's low profile. And the switch that I was talking about, so this switch does not exist. So what we did, we actually came up with a MEMS based switch. So you know that these are all waveguide structures. If you remember your BSc waveguide, you must have done electromagnetic class. And waveguide is actually a high profile, high pass filter. There is a cutoff frequency for each of these waveguide, rectangular waveguides or whatever waveguide you take. So, which means that beyond certain frequency, if you change the A dimension of the guide, so let's say a rectangular waveguide T10 mode, the cutoff frequency for that C over 2A, that A dimension of the guide. So if you change the A dimension of the guide, then your cutoff frequency changes. So if you can insert a septum in a waveguide where you change the A dimension of the guide, that will change the cutoff frequency, which means you can turn it on and off. So that's what we did using a MEMS structure. So in this one, I'll show you a video, but in this, what you see, this rectangular, orange rectangular, there are two waveguides, and there is some, arm going in and out. That is the septum. We just, if we insert one of them, the arm, then this waveguide gets cut off. That means does not transmit anymore. Other one opens up, so that we use either of them, and that we can use to do the calibration. So let's see if, so this is you just look at this, the arm is going in and out. This is under microscope video. And then that's how this MEMS structure works. And it works really well. The dimension of this orange rectangular metal waveguide is 250 micron by 500 micron. Thickness of your hair is about 150 micron. So these waveguide structures is just a couple of hair thick, and they're in metal, which means we are cutting metal with a piece of hair. So that's where the challenges lie. You have to have all the correct dimensions and all, and it worked very well. And we have a patent for this as well. So that is one of the things that we solved. And also we did, using piezoelectric motor, not MEMS. We also came up with another kind of switch structure that you can see that if you have a U structure in a waveguide, and if you just move them from one to the other, then this one turns on, this one is off, and then you can have much higher isolation. One of the challenge was that since these are metal structure, you cannot have metal to metal rubbing against each other. You have to put a gap. But if you put a gap, then the electromagnetic wave, they leak out, right? So how do you prevent that? So then you have to do EBG structure, that electromagnetic band gap structures, means you have some quarter wavelength, very precise, holes. That means waveguide that will prevent the leakage of all this. So we built it, and this, you can see here, it gave 80 or 90 dB of isolation between these two ports. So that is very important for radar applications as well. So and performed really well. You can see that these are all measured performances, less than 0.5 dB of insertion loss at this frequency is amazing. So this is also, we have this is the actual build structure that we did, and they took the cover off. And you can see here how this worked at precise alignment between these waveguides has to work as well. So a lot of challenges, but it worked really well. So we have switch that is working, and the SoC based synthesizer and the spectrometer, as I talked about, we actually developed SoC is system on a chip. So on your phone, if you have a smartphone, I know all of you have smartphone, you should open your smartphone if you have not done it yet. I did. I opened my wife's, smartphone. Of course, that because that was water damaged, and you will see that there are a lot of different SoCs out there, system on a chip. So, but this one they are working at 5 GHz, but we needed to make a synthesizer that is working at 90 GHz, W band. So we went ahead and designed the entire chip, and this is the chip. Let me turn on my pointer again. So this is the chip SoC, and this is the surrounding board that we made, the waveguide interface at W band. A synthesizer, if you buy a synthesizer at this frequency from Keysight or any other companies, it will draw at least 10 watts of power. So we cannot use this when my total instrument power budget is 5 watts. So we actually built it ourselves, and this one is drawing half a watt of power and beautiful performance. You can, this is a phase noise performance of this. And then the spectrometer chip is off the shelf spectrometers at these frequencies with 3 gigahertz bandwidth, 4096 channels. If this is a kind of spectrum analyzer that you use on your lab. It is huge, massive. It draws huge amount of power, 15 watt, 10 watts. So, but we build a 3 gigahertz spectrometer which draws 1.5 watts of power. And this is the actual gas cell measurement in the lab at 557 water line. You can see, as you know, as I was mentioning, we want to measure 557 water. So we can measure it really well with very high fidelity and high resolution. So that's what we have succeeded, and everything we had to put together for an instrument. This is WhatsApp instrument in a kind of CubeSat frame. That we have built two of them, one with this reflector antenna that we developed, and one with is the other antenna that's lens-based antenna. You can see here both those two, and then this is in our lab to give you a sense what is the size of this instrument. Let's see how I'm doing on time. Okay, 7:50, and I'll be ending soon. And then we also wanted to actually fly it on a balloon. This is a gondola. This instrument we put on a balloon that goes up to 120,000 feet. And you can see here we've had two such flights. This is the day we are flying. The flight, we have to go there at 3 a.m. because balloon flight launch always happens early in the morning when the air is very calm. And we put it on the balloon, and you can see here, this is the launch video of our balloon. You can see this is a handheld. This is, we release it, and that's where our instrument is here. This is the people who are actually holding our instrument is going up, and then they release, there goes up, and it flies up to 120,000. Here, there is the transmitter that gives the data, the health of this instrument. And this is the pi balloon that actually tells us what is the air speed, velocity at the time. So then it goes up. It launched very well, and then it went there and did some measurement. And unfortunately, they have a small parachute, but the parachute did not work very well. So our balloon afterwards, it landed at 40 miles per hour, so crash landed. So only thing happened is the lens broke, but all other parts of the instrument, this is the after we recovered our instrument after it crash landed. You can see only the lens broke, but everything inside survived. Kind of a shock test that we did. And so we brought it back to our lab and tested everything. It was working perfect, no problem. And it is the flight path of this. We launched it from Palestine, Texas, and it went quite a bit towards Dallas, and then we recovered from there. And we are not measuring water because water line is too strong and pressure broadened that it saturates our instrument on Earth at 120,000 feet, but on space it is fine. So we measured ozone line, O3. You can see here We did the spectroscopic measurement of the ozone and validate the instrument. That instrument really worked. So it really worked well. So we are ready now to launch our, when you get a ride, we can actually launch our WhatsApp instrument to answer this question that did comets brought water to Earth once for all. So that will be very exciting thing. I'll end with this slide. Many of you know about Mars helicopter. I'm not going to talk about it, but it actually on January 18th this year, the helicopter had its last flight. We had done 72 flights. When we built the helicopter, it was supposed to have only, three to four flights, but it did 72 flights. And I just wanted to end with that, rest in peace, Ingenuity. It did amazing. It was such a great small instrument. Thank you. Thank you very much for listening in, and I'll be more than happy to answer some questions.
Okay, so thank you so much. It was really an interesting talk, and we got to learn so many things and about so many ongoing experiments at NASA. Thank you. So, I'm looking at the chat box now if we have any questions there. I don't see any.
You can turn on, if you have any question, you can turn on your video, audio, and then ask as well.
Yeah.
Wow, no questions. Not about Area 51.
Okay, so we have one question in the chat. It is by Shantanu Sinha. What is the noise figure you target at 500 gigahertz?
Yes, a very good question, Santanu. That, of course, in when we are talking about these very sensitive instruments, we mostly talk not in noise figure, talk about noise temperature, because you know that F minus 1 times your 300 Kelvin gives you the noise temperature. And we can convert noise figure to noise temperature. So noise temperature of the system noise temperature, double sideband system noise temperature for this instrument was about 3000 Kelvin. That is not the mixer for the entire instrument, so it includes all the losses in the entire system. So that is very sensitive. That is the most sensitive room temperature instrument that you can develop at this frequency. So mixer noise temperature is about, on this one is slightly higher, about 1500 1600 Kelvin. Then you have this loss of the switch up front, so you'll have to add those, right, the Friis formula, and then you get about 3000 Kelvin noise temperature. You can convert it back to noise figure.
I hope that answered your question, Shantanu. So we have another question from Shomujit Boshak. How can we determine the habitability of a planet located 4 light years away when direct physical exploration is not possible? What parameters are assessed in this process?
Yeah, again, very good question, Somaji. Thank you. So what happens is, okay, I did not show on slide that what we measure, right? What we are see, we don't even measure directly light from these planets. Our instruments are not sensitive enough. So what we do, how we find the existence of these planets is actually indirect way. There are various ways one can do. One is called transit time method. What we do is we actually isolate that light that is coming from that particular star where the planet exists. That is not an easy thing to do. How do you really isolate all the other light that's coming in the background, and then just measure the total amount of light that is coming from that particular star? And then whenever the planet goes in front of it, of course, the planet has to be going, has to be in our line of sight. And then the total amount of light dips a little bit as the planet goes around it. And if your detector is sensitive enough, it can actually capture that. And by measuring that dip in the total amount of light, we can tell that, okay, there exists a planet. And also we can actually get so much of information from there is that, okay, looking at how long it took to go cross that what's the orbit of that, right? And from there, we can also find out that how far the planet is from that star. And from there, we can find out if, because of your centrifugal forces calculation, you can say, okay, then what will be the mass? We know the mass of the star, and then what will be the mass of this planet. Now, knowing the mass of the planet, we can also find out from these measurements itself what is the volume of this planet. If you know the mass of the planet, you know the volume, then you can find out the density of this. If you know the density, then you can actually find out, okay, if it is a gaseous planet or it is a rocky planet. And also you can find out that what will be the surface temperature of this. Given the distance, we know how bright the star is. We know a lot more about the star because we can do the measurement than the planet. But all this thing is done in an indirect way, right? We know the surface temperature, but we still don't know what if there is an atmosphere or not of this planet. So that's what we are doing the next. The next phase of study is there an atmosphere? Is there oxygen? Is there hydrogen? Is there water vapor in that? So those part we are still not able to do, but all these other stuff that we can do. So if that we know the surface temperature, then we can say if there is water, then the water at the surface will be in liquid form or not. So those things we can do. Only some simple measurements from our satellites or from planet Earth. We can do those kind of. This is the process. These are the parameters that we look at and say, okay, this is habitable. But it's not enough, as you might realize, that we'll have to then do the next phase of studies about spectroscopy of the atmosphere to find out what is there, what kind of atmosphere. Is it like Titan is all full of methane, or is it like our atmosphere, mix of nitrogen, hydrogen, might oxygen, and all those stuff. So that's what we have to do, and that is the process we follow.
Great. Thank you.
I had a
I think,
question.
yeah, sure. Go ahead.
Okay, thank you so much for the wonderful talk, sir. And I had this question. I was wondering about this. Like, if we want to measure from Earth on ground, like the water vapor on in the Earth's atmosphere, what will be the ideal antenna design for that? Like,
So what exactly you are trying to measure, Arjun?
say
Say it again.
we want to measure the water vapor in the Earth's atmosphere. For that purpose, like on ground.
So, so people are doing it actually. When you do is you measure the water vapor for many experiments, particularly for, of course, a radio astronomy experiment, because water absorbs many of these signals that you are trying to measure, right? The one of the measurement that you mostly do from Earth, sitting on Earth, is at 183 gigahertz, because water has strong line at 180. We don't do at 557 because 557 is very pressure broadened on Earth, because since it's such a strong line, it becomes so broad towards the end that it completely saturates your instrument. But 183 gigahertz line is not as strong. So you can use any antenna at 183 gigahertz you want. You can do a reflector antenna if you don't have any constraint on your volume. Reflector is the best antenna to use because it has very high gain, very high efficiency. But you can use any other antenna. But 183 gigahertz patch antenna you can use, but they're lossy, because their metal patches are lossy. So it more comes down to not about the antenna, but about what kind of detector that you are going to use, what kind of sensitivity that you need. If you are doing room temperature at 183 gigahertz, you can use Schottky based room temperature detector, receiver, heterodyne instrument you can put together, and use a reflector antenna or a patch if you can tolerate some losses. So that's how we can do the measurement.
Okay, thank you.
We have few more questions in the chat box. So
Yeah,
that
there is
will,
a question from Tithi, right?
yeah. So it is, could you please elaborate again on the low profile, high gain, leaky wave lens
Lens
antenna?
antenna. Okay, good question. So, see, what happens is if you look at a lens antenna, so lens antenna is similar to the lenses that you use in optical frequencies, but they are thick. So if you look a plano, sorry, let me just drink a little bit. If you do a plano convex lens, with normal lens, it is very heavy. We don't want to do that because we want to avoid mass. So instead, we in this at these frequencies we use high resistivity silicon. Why high resistivity silicon? Because if you use low resistivity, then it will absorb the power. Its losses will be very high. High resistivity silicon, the transmission loss is almost negligible at these frequencies. So idea is that you take a very thin lens of very high aperture, very thin lens, right? Now you have to illuminate that lens. When you are illuminating that lens, if you try to illuminate the entire, like this is 18 centimeter aperture. So if you have to do 18 centimeter aperture, if you have to use a normal way, how do you illuminate a normal way of lens? Maybe you can use a horn antenna. However, because the way the horn antenna radiates, you'll have to put the horn antenna quite far, below the lens. Then it is not a low profile anymore. Then you'll have to come up, okay, what kind of feed that I can use? If you think about leaky wave feed is that it kind of generates a surface wave that actually leaks. It actually goes, across it. So you'll have to have the feed, and there's an air gap, and there the wave they actually go. This is called leaky wave because it kind of leaks and goes on the sideways. And then if you look at the radiation pattern of that is very broad in the sense we can illuminate the entire 18 centimeter, 20 centimeter aperture, where even if we put the feed very close to the lens, that's how we can illuminate the entire lens structure and gets very high efficient. That's why we use a leaky wave feed for illuminating this lens antenna. I hope I answered your question.
Okay, so we have one last question from CD Joseph Nicholas. He says, for Europa, you said the ice thickness is between 15 to 100 kilometer and traveling distances of 7 years. I want to ask at what speed for the device and what fuel can do this?
Yes. So basically, for you're asking about a rocket question. So first, these are chemically. Most of the time, we are using chemical, rockets. So for if you when you are actually going, first challenge is you'll have to get out of our gravity, and given the mass, and also you'll have to just go. And once you are out of our gravity, the bigger the rocket, then the speed of this cruising speed of these rockets is about 77 to 80,000 kilometer per hour that I mentioned before. So it is all fueled by chemical rocket fuel. However, recently we have come up with electric propulsion, and these are thermoelectric propulsion systems, and there it cruising speed is slightly less. However, it can actually go farther because it doesn't take as much of the mass. So you have to carry tank of fuel whenever we are going using chemical rocket technology. So for the Psyche mission that is going to an asteroid, for that we have used for the first time electric chemical propulsion. Thermoelectric propulsion, electric propulsion system.
Okay, great. I think, okay, all right. We have another question from Shubho Broto. In terahertz communication, high power handling is required. So, how we deal with the ability to control signal path loss?
Okay, for communication, we do not use really terahertz, and you are correct because terahertz frequencies are very lossy through the atmosphere. because of primarily of the absorption by water, oxygen, those particular frequencies. Some of the windows are available where the path loss is manageable, but other frequencies. So you are not going to get, very long distance terahertz communication because it is high path loss. However, you can do short distance, very high speed communication with terahertz. So one of the places where it's really being looked into in your backhaul of your modern day communication, because from your tower, because of the explosion of handheld these phones and everything, you'll have to have so many different systems connected. So from there to connect it to the processing in the backside, you need huge bandwidth. That is not possible at existing low frequency system, but terahertz gives you huge bandwidth, right? And so what we do, I know the distance is short distance, so we are looking into most of the systems that you see 5G systems will be using terahertz as their backhaul. The short distance, very high speed, very high data rate, very high bandwidth system. So that's what we are going to use. I think we exhausted all the questions.
Okay, Shubhabrata has another question. For terahertz, we can use attenuator to control the path loss.
You cannot use attenuator to control path loss because attenuator will be using to do the other thing, right? First of all, have you looked into building an attenuator, control attenuator terahertz frequencies? It does not exist. We just our paper got accepted on a variable attenuator at terahertz. It does not exist. And also, but it is needed system because when you're building any system, you need all these components. Attenuators are needed because if you don't have an attenuator, you won't be able to control the way for the terahertz frequencies. If you're building a heterodyne system like 557 gigahertz system, you need to have controlled amount of power that is going into the mixer to do a mixing process, right? It's a heterodyne system. But how do you control the power at terahertz frequencies? If you look around, there is no, uh, attenuator available at 557 gigahertz. So these are the challenges working at terahertz frequencies, that you need a component you see that it does not exist, that you'll have to come up and for the first time builds that that component. So that's what we have been doing, past 20 years, that build all these phase shifters, attenuators and stuff. So that's where the challenge lies.
I think that answers your question, Shubhabrata. Uh, do we have any more questions? You can unmute yourself and directly
Ask the
ask your.
question directly. Yeah, there is a question. You said that Mars has no traces of water. No, I didn't say that. What I said that Mars does not have a flowing water now, but we have water. We found water on Mars. We have found water underneath of Mars. One of the biggest questions that people have, that all this water that Mars had, where did it go? What is the process that Mars lost water? So it is still not a settled answer yet. And that, but there is multiple theories. One of the thing that happened is because Mars density of Mars atmosphere is just 1% of planet Earth. As a result of all these high cosmic rays that comes in through the space, that actually penetrated the atmosphere and split the water into hydrogen and oxygen, and that majority of the water that we lost in Mars through that process. However, it turns out some of this water got absorbed, and all these different, in the earth, all the different minerals and all, they are containing quite a bit of water underneath the surface of Mars. And we found maybe some pool of water underneath the surface, some places. But what I was trying to emphasize on, that we do not have flowing water, like let's say in go to Kolkata, outsides of Kolkata, you will find a lot of pukur kind of things. We don't see that kind of water, or in the rain, that all the flowing water that comes in. We don't see that kind of water, but there is traces of water on Mars.
Okay. Okay. So I think we are almost towards the end of our session. I have one last organizational question. Sir, would you be comfortable sharing your slides with the attendees?
These slides are very large because of given some videos and a lot of high, very high quality image. So email sharing is not possible. So it's kind of difficult. So I'll prefer that if you have questions, just write to me. I'll try to answer. That will be a better way to handle.
Sure, sure. That would be great. So, yeah, let's again thanks our distinguished speaker once again for the wonderful talk. And to all our attendees, thank you for your active participation and for choosing to spend your weekend with us. And I would like to specially thank the team members for helping organize this webinar. Yeah, I think that's it. And to the attendees again, keep an eye on our social media channels for announcement about our next events. Again, thank you all for being here today.
Thank you. You have a good dinner wherever you are, lunch, dinner, and I'll go and have my breakfast. Bye.
Yeah, sure. Thank you, sir. Bye.